In my previous classes, I have discussed about the triangle law of additional vectors and parallelogram law of additional vectors. I have also discussed some special cases in the parallelogram law of addition of vectors, and I have discussed some problems based on the parallelogram law of addition of vectors and triangle law of addition of vectors. So next I am going to discuss about components of a vector. So in general, if the vector sum of two or more number of vectors gives you the vector r bar, then those vectors whose vector sum gives you the vector r bar can be called as the component vectors of r bar. Okay, components of a vector. Now, as I discussed in the parallelogram law of vector addition, suppose if two vectors p bar and q bar are represented graphically by the adjacent sides of the parallelogram, such that tail of p bar is attached to the tail of vector q bar. Then the diagonal of the parallelogram passing through their point of intersection represent the vector sum of p bar and q bar, or resultant of p bar and q bar. In the parallelogram law of addition of vectors, the vector sum of p bar and q bar we have denoted by r bar. That means if the two vectors p bar and q bar are represented graphically by the adjacent sides of the parallelogram, such that tail of p bar is attached to tail of q bar, and the diagonal of the parallelogram passing through their point of intersection represents the resultant of p bar and q bar, which I have denoted by r bar. We can write here p bar plus q bar equal to r bar in the figure. We can call p bar and q bar as the component vectors of vector r bar. P bar and q bar can be called as the component vectors of r bar. It's not necessary that there are only two components for a given vector. Suppose if the vector sum of three vectors a bar, b bar and c bar gives you the vector r bar, then the three vectors can be called as the component vectors of r bar. That means in general, those vectors whose vector sum gives the vector r bar can be called as the component vectors of r bar. So initially in our applications, we discuss only about two components of vector. Therefore, in general, if the vector sum of two vectors as shown in the figure p bar and q bar gives you the vector r bar, then the two vectors p bar and q bar can be called as the component vectors of r bar. So any two vectors whose vector sum gives you the vector r bar can be called as the component vectors of r bar. If one component of vector r bar is suppose perpendicular to the other component, then the two components are called as the rectangular components of the vector. You see, one component of the vector, suppose perpendicular to the other component of the vector, then the two components can be called as the rectangular components of vector. So next I am going to discuss how a given vector can be expressed in terms of its two rectangular components and the unit vectors along the coordinate axis. Suppose if a vector r bar makes an angle theta with a positive direction of x-axis, let us suppose the vector r bar lies in the xy plane. That means we are discussing about how to find the two rectangular components of vector in two dimensions. Then to find the rectangular components of the vector along the two coordinate axes, you have to construct a rectangle with adjacent sides parallel to x and y axis such that the vector r bar acts along the diagonal of the rectangle. So in general, to find the two rectangular components of a vector along the coordinate axis, x-axis and y-axis, we have to construct a rectangle with adjacent sides parallel to x and y-axis such that the vector r bar acts along the diagonal of the rectangle. So in this figure, the directed line segment OC bar represents the vector r bar, which makes an angle theta with a positive direction of x-axis. OACB is a rectangle. So every rectangle is also a parallelogram. Therefore, OACB is also a parallelogram. From parallelogram law of addition of vectors, the vector sum of OA bar and OB bar will be equal to the OC bar. So from parallelogram law of addition of vectors, of two vectors, we can say that vector OC bar equal to vector sum of OA bar and OB bar. The vector OC bar is equal to the vector sum of OA bar and OB bar. Now here the directed line segment OC bar represents the vector r bar. As I told you before, the vector sum of two vectors gives you the vector r bar. Then the two vectors can be called as the component vectors of r bar. Here the vector sum of OA bar and OB bar gives the vector r bar. Therefore, the two vectors OA bar and OB bar can be called as the component vectors of r bar. The component vector OA bar is perpendicular to the component vector OB bar. If the two components are perpendicular to each other, then they can be called as the rectangular components of the vector R bar. So OA bar and OB bar can be called as the rectangular component vectors of the vector R bar. The component vector OA bar, which acts along x-axis, is called as x component vector of R bar, which is denoted by Rx bar. The component vector OB bar, which is parallel to the y-axis, is called the y component vector, which is denoted by Ry bar. So I have again drawn the same diagram which I have shown you in the previous discussion. As I told you, the OA bar and OB bar can be called as the component vectors of vector R bar. Vector R bar is represented by the parallelogram law of addition of vectors along the direct line segment OC bar. Now from parallelogram law of addition of vectors, OC bar can be written as OA bar plus OB bar. OA bar and OB bar can be called as component vectors of OC bar. So here OC bar represents the vector R bar. The direct line segment OA bar is called x component of the vector R bar, which is denoted by Rx bar. The component OB bar, which is directed parallel to the y-axis, is called y component of the vector R bar, which is denoted by Ry bar. So we can write R bar equal to Rx bar plus Ry bar. So Rx bar and Ry bar, they can be called as vector components of R bar. As I discussed earlier about the term unit vector, a vector having unit magnitude is called a unit vector. As I discussed previously, that any vector can be expressed as the product of its magnitude and the unit vector in the same direction. Any vector can be expressed as the product of its magnitude and unit vector in the same direction. The unit vector which acts along the positive direction of x-axis is denoted by I bar. The unit vector which acts in the positive direction of y-axis denoted by J bar, or you can also write J cap. So the unit vector which is direct along positive direction of x-axis denoted by I bar or I cap. The unit vector which is directed along positive y direction denoted by J bar or J cap. As I discussed in the past, any vector can be expressed as the product of its magnitude and the unit vector in the same direction. So the component vector Rx bar can be written as the length of the line OA into I bar, or we can write length of the line OA by denoted by Rx. The component vector Rx bar acts along x-axis, and unit vector in this direction is denoted by I bar or I cap. So the component vector Rx bar can be written as product of its magnitude and the unit vector in the same direction. Similarly, the component vector Ry bar, which acts along the y direction or parallel to the y direction, can be written as length of the line OB into J bar. That is written as Ry into J bar. So you can substitute here in this equation Rx bar equal to Rx I bar and Ry bar equal to Ry into J bar. Therefore, in two dimensions, the vector R bar can be expressed as Rx into I bar plus Ry into J bar. This Rx and Ry, they are called scalar components. This Rx and Ry, they are called as scalar components of vector R bar. Whereas Rx bar and Ry bar, that means Rx I bar and Ry J bar, they are called vector components of vector R bar along x and y axis respectively. Now see, in the figure OACB is rectangle, so OAC is right angle triangle. So if you apply Pythagoras theorem for the right angle triangle OAC, we can write OC square equal to OA square plus AC square. So in rectangle, opposite sides are equal in length. So length of the line AC is same as the length of the line OB. Therefore, we can write OC square equal to OA square plus OB square. So the length of the line OC gives you the magnitude of the vector R bar or modulus of vector R bar. The length of the line OA gives you the Rx. The length of the line OB will be equal to Ry. Therefore, square of the magnitude of vector R bar is equal to square of the magnitude of the x component plus square of the magnitude of the y component. So in general, a vector R bar which lies in the xy plane in two dimensions can be written as R bar equal to Rx I bar plus Ry J bar, where I bar is the unit vector along positive x direction, J bar is the unit vector along positive y direction. This Rx and Ry, they are called scalar components of vector R bar along x and y axis. And magnitude of vector R bar will be equal to under root of Rx square plus Ry square. You can just go through the discussion. Again, in some problems we express the two rectangular components of the vector r bar in terms of the magnitude of the vector r bar and the angle theta which the vector r bar makes with one of the coordinate axes. In the given figure, theta is the angle made by the vector r bar with x-axis. So I have drawn the same rectangle which I have shown in the earlier diagram. The same rectangle again I have shown here. That means OACB is the rectangle. OA is the x component and OB is the y component of vector r bar. The vector r bar is represented by the directional line segment OC bar. So here OACB is the rectangle and OAC is the right angle triangle. So in the right angle triangle, OAC, cos theta equal to length of the side adjacent to the angle theta divided by length of the hypotenuse side. So in the right angle triangle OAC, cos theta can be written as length of the side adjacent to the angle theta divided by length of the hypotenuse side. So cos theta can be written as OA by OC. Now in the figure, length of the line OA is equal to Rx. And length of the line OC gives you the magnitude of vector r bar. Therefore you can write cos theta equal to Rx by modulus of vector r bar. Therefore you can write Rx equal to mod of r bar into cos theta, or we write simply Rx equal to r cos theta. So if the vector r bar which lies in the xy plane makes an angle theta with the positive direction of x-axis, the next component of the vector is given by Rx equal to r cos theta. In the same triangle again OAC, can write sin theta equal to the length of the side opposite to the angle theta divided by length of the hypotenuse side. So here AC is the side opposite to the angle theta, OC is the hypotenuse side. Again in the same triangle OAC, sin theta you can write AC by, length of the line AC divided by length of the line OC. So in rectangle, in the rectangle OACB, opposite sides will have same length. So AC can be written as OB. Now length of the line OB gives you the y component of r bar denoted by ry. And the length of the line OC gives you the magnitude of vector r bar. So sin theta can be written as ry by modulus of vector r bar. So ry can be written as modulus of vector r bar into sin theta. So ry can be written as r sin theta. That means if the vector r bar makes an angle theta with the positive direction of x-axis, I mean, if the vector r bar lies in the xy plane and makes an angle theta with the positive direction of x-axis, then the x component of the vector is given by rx equal r cos theta. The y component of the vector can be written as ry equal r sin theta. So, just I have discussed that if the vector r bar makes an angle theta with the positive direction of x-axis, the next component of the vector will be equal to r cos theta, and the y component of the vector is given by ry equal to r sin theta. So in general, if a vector r bar is resolved into two rectangular components, then the component that makes an angle theta with the direction of with the vector r bar, that is equal to r cos theta, and the other component will be equal to r sin theta. While solving numerical problems in mechanics, starting from Newton's laws of motion, we resolve the forces into rectangular components in many problems. So some of the students are unable to do the resolution of the force into components in the solution of problems in Newton's laws. They think that always horizontal component is r cos theta and vertical component is r sin theta. So you should not remember that way. You should remember that the component that makes an angle theta with the direction of the given vector r bar, that is r cos theta. The other component is r sin theta. For example, in one of the problems in Newton's laws, if you have a situation like this, a pulling force F bar acts at an angle theta with the vertical direction on a block of mass resting on the horizontal floor. That means the figure I have shown here lies in the vertical plane. This diagram is in vertical plane. This force F bar, suppose, acts on a block of mass m at an angle theta with the vertical direction, and this block is resting on the horizontal floor. And in the solution of the problem, we may choose. I am not solving a problem at present. I am only discussing how to resolve a force into rectangular components, into two rectangular components in different situations. Suppose if we choose the horizontal direction as x-axis and vertical direction as y-axis, then to resolve this force into two rectangular components parallel to x and y axis, we have to construct a rectangle with adjacent sides along x and y axis such that the force F bar acts along the diagonal of the rectangle. Then this component which makes an angle theta with the direction of the force, or the component that is adjacent to the angle theta, that should be taken as equal to F cos theta. The other rectangular component will be equal to F sin theta. That means in this example, vertical component of the force which is directed along y-axis has magnitude F cos theta. The horizontal component of the force has magnitude F sin theta. Suppose if you consider another example We come across all similar situation in the problems in Newton's laws and other topics in mechanics. For example, if a pushing force F bar acts on the block in this direction, that means here also the figure lies in the vertical plane. This block of mass is resting on the horizontal floor. The pushing force F bar is applied on the block at an angle theta with the horizontal as shown in the figure. So to resolve this force into two rectangular components, in the solution of the problem, we can draw a given vector at a different place in the figure without changing its magnitude and direction. Two vectors are said to be equal if they have same magnitude and same direction. So graphically, you can represent a given vector parallel to itself at a different place in the diagram. So I can draw a direct line segment like this, which represents vector of same magnitude as this in the same direction. So this is F bar. So to resolve this vector, I mean the force F bar, into rectangular components along the horizontal and vertical directions, we have to construct a rectangle with adjacent sides along the horizontal and vertical directions such that the force F bar acts along the diagonal of the rectangle. So this angle will also be equal to theta. So this component which makes angle theta with the direction of the force, that will be F cos theta. The other component will be equal to F sin theta. That means in general, if the force F bar is resolved into two rectangular components in a plane, then the component which makes an angle theta with the direction of the force is F cos theta, and the other rectangular component is F sin theta. Again, going to the first diagram, if the vector r bar lies in xy plane and if it makes an angle theta with the positive direction of x-axis, then Rx equal R cos theta, Ry equal R sin theta. So keeping the magnitude of the vector fixed, suppose if we increase this angle theta made by R bar in the first figure with the positive direction of x-axis, then magnitude of the x component will decrease, magnitude of y component will increase. So here Rx will be equal to R cos theta. Of course, Ry is equal to R sin theta. Suppose if the vector R bar acts along y direction, along y axis, then the angle theta made by the vector with x-axis will be 90 degrees. Then mathematically writing, Rx equal to R cos theta, that means R cos 90 degrees. That is 0. Ry equal to R sin theta, that is equal to R. So in general, vector R bar which lies in the xy plane can write Rx I bar plus Ry j bar. So in this figure, I mean when vector R bar acts along y-axis, Rx is 0, Ry equal to R. So R bar you can write Rj bar. That means if a vector is directed parallel to the y-axis, then we can say that its rectangular component along the x direction is 0. Similarly, if a vector is directed parallel to the x-axis, we can say that its rectangular component along the y direction is 0. That means in the same figure, the starting figure, I have used letter theta to denote the angle made by the vector R bar with x-axis. Suppose if theta is 0 degrees. I mean if the vector R bar acts along x-axis. If theta is 0 degrees, it means vector R bar acts along x-axis. Then Rx will be equal to R cos theta or R cos 0 degrees, that is equal to R. Ry equal to R sin theta or R sin 0 degrees, that is 0. So if a vector is directed along x-axis, you can say that its rectangular component along y direction is 0. So in this case, R bar can be written as R I bar. So in general, a vector will have no rectangular component in a direction perpendicular to it. If a vector is parallel to the x direction, you can say that its rectangular component in the y direction is 0. Similarly, if a vector is parallel to the y direction, then we can say that its rectangular component along the x direction is 0. Now, I would like to once revise whatever I have taught so far in the rectangular components of vector. So now, I would like to once revise the discussion I have done about the components of vector. If the vector sum of two vectors gives the vector R bar, then the two vectors can be called as the component vectors of R bar. If one component is perpendicular to the other component, then the two components are called as the rectangular components of the vector R bar. So in the figure, the direct line segment OC bar represents the vector R bar and OACB is rectangle. That means here, this is the diagram I have discussed for rectangular components of vector in 2 dimensions. I mean vector R bar lies in the xy plane. In the figure, the direct line segment OC bar represents the vector R bar and OACB is rectangle. And OA from CB is rectangle is also parallelogram. From parallelogram law of addition of vectors, we can write OC bar equal to OA bar plus OB bar. Or we can write R bar equal to Rx bar plus Ry bar. There OA bar is Rx bar and OB bar is Ry bar. We can write Rx bar equal to Rx into I bar and Ry bar equal to Ry into J bar. Rx bar and Ry bar are called as vector components of R bar. Of course, I bar is a unit vector along positive x-axis. J bar is unit vector along positive y-axis. So in the right angle triangle OAC, cos theta equal to OA by OC. Length of line OA equal to Rx and length of line OC gives you magnitude of R bar. So you can write cos theta equal to Rx by magnitude of R bar. Or you can write Rx equal to R cos theta. Those who want to write the notes, they can take a pause and write the notes if you feel it is required. Again, the same triangle OAC, sin theta equal to length of the side AC opposite theta divided by length of the hypotenuse side OC. Rectangle OACB, opposite sides have same length. So length of side AC will be same as the length of the side line OB. So you can write sin theta equal to OB by OC. Now OB gives you Ry, length of line OC equal to mod of R bar. So sin theta equal to Ry by mod of R bar, or you can write Ry equal to R sin theta. So Rx equal to R cos theta, Ry equal to R sin theta. The same triangle again OAC, if you apply Pythagoras theorem, you can write OC square equal to OA square plus AC square. In the rectangle OACB, length of side AC same as length of side OB. So the Pythagoras theorem I have written previously, OC square equal to OA square plus AC square. Now we can write AC equal to OB. Therefore we can write OC square equal to OA square plus OB square. Length of line OA gives you Rx. Length of line OB gives you Ry. Rx and Ry, they are called the scalar components of vector R bar along x and y axis. Usually, when we just say components of vector R bar along x and y axis, we usually mean the scalar components Rx and Ry. So square of mod of R bar, you can write Rx square plus Ry square. So in general, in 2 dimensions, vector R bar lying in xy plane can be expressed as R bar equal to Rx I bar plus Ry J bar. And mod of R bar is given by under root of Rx square plus Ry square. Rx comma Ry are called as scalar components of R bar. When a vector R bar is resolved into 2 rectangular components, then the component which makes an angle theta with R bar is R cos theta and the other component is R sin theta. A vector will have no rectangular component in a direction perpendicular to it. Suppose if a vector is directed parallel to the x-axis, then its rectangular component along y direction is 0. If a vector is directed parallel to y-axis, then its rectangular component along the x direction is 0. So look at this problem based on resolution of the force in 2 rectangular components. I will read out the problem. A force F bar is resolved into two rectangular components along the horizontal vertical directions, and the magnitude of the vertical component exceeds the horizontal component by 20 Newton. If the force makes an angle of 37 degrees with the vertical, then find the two components of the force. You have to take sine 37 degrees equal to 3 by 5. If you want, you can take a pause and try the problem. Otherwise, look at the solution of the problem. So now look at the solution of the problem. So given that the force F bar makes an angle theta, which is equal to 37 degrees with the vertical direction. You are asked to find the two rectangular components of the force along the horizontal and vertical directions. So this is the horizontal direction and this is the vertical direction. The force F bar lies in a vertical plane here. To resolve the force F bar into two rectangular components along the horizontal and vertical directions, you have to construct a rectangle with adjacent sides of the rectangle along the horizontal and vertical directions, such that the force F bar acts along the diagonal of the rectangle. So this component of the force which makes angle theta with the direction of the force F bar, that is the component which is adjacent to the angle theta, will have magnitude F cos theta. And magnitude of other rectangular component will be equal to F sin theta. So it's given that the magnitude of the vertical component exceeds the magnitude of the horizontal component by 20 newtons. That means magnitude of the vertical component is F cos theta. That is more than the magnitude of the horizontal component by 20 Newton. That means F cos theta minus F sin theta equal to 20 newtons. Here theta is given to be 37 degrees. You can take F common here. Theta is given to be 37 degrees. So you are given that the value of sine 37 degrees equal to 3 by 5. From that you can find the value of cos 37 degrees yourself. It comes out to be 4 by 5. So you can substitute cos 37 degrees equal to 4 by 5 and sine 37 degrees equal to 3 by 5. So from this you get F into 1 by 5 is 20 newtons, or F is equal to 100 newton. So the magnitude of the force is 100 newtons. Now you are asked to find the two rectangular components of the force along the horizontal and vertical directions. So horizontal component of the force is equal to F sin theta. Here theta is 37 degrees, or F sin 37 degrees. Here we got F as 100 newtons Sine 37 degrees equals 3 by 5. So that will be equal to 60 Newton. So that is one of the answers. So magnitude of the vertical component of the force will be equal to F cos theta. Here theta is 37 degrees. So we got F equal to 100 Newton and cos 37 degrees equal to 4 by 5. So you get magnitude of the vertical component as 80 Newton. So that's the answer. It means magnitude of the horizontal component of the force is 60 Newtons and magnitude of the vertical component of the force is 80 Newtons. So in the next class, I am going to discuss about the addition of two vectors in terms of their rectangular components. That means I am going to discuss how the components of resultant vector can be expressed in terms of the components of the two vectors in the next class.